You should be able to start. Okay.
Okay, awesome. So hello, everyone. Not a lot of you here today, but we're going to go over relations, functions, and combinatorics. So let's look at our first problem. We have A is a cross product of two sets, and B is n, such that n is a positive factor of 144. And we have a function with the rule that, this rule right here. Okay, so first we want to prove that f is 1-to-1. And before we get into that, let's just make sure that we understand what this function is, because it's kind of confusing with the cross product and everything. So just remember that this f of ab, that a is a product, a is an element of this set, and b is an element of this set. The ordered pair itself is the input, and it's the domain, and our codomain is going to be whatever is the product of these two numbers. So we want to prove that f is 1-to-1. All right, and remember that to prove that something is 1-to-1, we want to show that for every x and y that are in A, if f of x equals f of y, then x equals y. And there is another way to explain 1-to-1. So does anyone want to explain the less technical version? Okay, so let's draw just really quick, just a couple of little. These are our domain and codomain. And let's say that that's our function. Is that 1-to-1?
Yes.
All right. Can you explain why?
Is it because every output only has one input that points to it?
Yeah, well, so this point right here actually has two
different
things pointing to it.
Oh, I thought there was.
So this function isn't going to be one. Oh, sorry. Here, let me erase that. We'll make it a little bit bigger so it's more clear. So you've got 3 dots here and 2 dots here. Okay, so this is not 1-to-1. Because some elements in the codomain have more than one element from the domain pointing at it. So yeah, your reasoning was right, just didn't draw the diagram big enough. Okay, so to prove that this function is going to be 1-to-1, we want to say, let's let f of a1, b1 equal f of a2, b2. And we want to eventually show that a1, b1 is equal to a2, b2. Okay, so with that, does anybody have an idea of where we can start with this problem? Okay, so if we're letting that these two functions are equal to each other, that means that 2 to the a1 times 3 to the b1 is equal to 2 to the a2 times 3 to the b sub 2. Okay, so now we remember that we're trying to eventually show that a1 is equal to a2 and b1 is equal to b2. So one way that we can manipulate this is if we divide both of these sides by the left-hand side of the equation. And this can simplify down to, because of the rules of exponents, we have 2 to the a1 minus a2 times 3 to the b1 minus b2. And that is going to equal 1. All right, now there's a way that we can kind of expand this right-hand side so that we can get what we want. Does anyone want to take a guess at what we can manipulate the right-hand side to be? It's something about the powers of 2 and 3. So we can set it to, let's see. That's going to be 2 times 2 to the something times 3 to the something.
0.
Mm-hmm. All right, and what this tells us is that a1 minus a2 equals 0, and b1 minus b2 equals 0. So we end up getting that a1 equals a2, b1 equals b2, and that means that a1, b1 equals a2, b2, which is what we wanted to show from the beginning.
I have a quick question. Why is it equal to 1 when A1 and A2 could be different? Couldn't they be different? And B1.
So do you mean this step right here?
Yes.
Okay, so we divided both of these sides by this term, by the right-hand term. So this whole thing simplifies down to 1 because it's the same thing over the same thing. And this side doesn't simplify down to 1, it simplifies down to this term, which we just used laws of exponents to get to.
Right, I get that, but if like on the step where it's equal to 1, that 2 to the A1 minus A2 times 3 to the B1 minus B2, if A1 and A2 were different and B1 and B2 were different, then it wouldn't equal 1, right? Like say A1 was 1
Yes.
and A2 was 2, you know? Wouldn't they have to be the same to get to 0 in order for them to be 1?
Well, so I think you're going backwards just a little bit. We know that this is true. We know that they are equal to 1. And the only way for this right-hand side to be equal to 1 is for both of these exponents to be 0, right? Because if they were different from each other, or if they were anything other than 0, then we would get that this isn't equal to 1, but we already know that that's true. So this is just kind of expanding 1 so that we have something that we can set these exponents equal to.
I just don't understand where the 1 is coming from.
The
How
1
do
is just
you
coming
know-
from these two on top of each other. Because we can divide, anything that we do to one side, we can do to the other. So we just divided both of these sides by the same term, and this one just happened to simplify to 1.
I see. Okay, sorry about that.
No worries. Questions are awesome. I love them.
Thank you.
Does that make a little bit more sense, or is
Yeah,
there anything else I can clear up?
It does now.
Okay, awesome. Are there any other questions on this proof? Okay, let's move on to, we want to prove that f is onto, and we have a hint, which is that the prime factorization of 144 is 2 to the 4th times 3 to the 2nd. Okay, so remember, let's just write down the definition of onto, which is that for every b in the codomain, there exists some a in the domain such that b is equal to f of a. Okay, and then let's draw a couple diagrams again. All right. So is this on too?
No,
And why not?
because not every point in the output is hit.
Exactly. And it's still a valid function because everything in the domain has an arrow coming from it, but not everything in the codomain has an arrow pointing to it. So we want to show that this is not the case. All right, so first let's kind of convert this into our problem, which is that we want to show that there is some f of AB that equals C if we let C be in the codomain. All right. I guess these are kind of actually reversed. Let's see here. I'm going to rewrite that to make it a little bit more clear. So we're going to let C be in the codomain, and we want to show that there is some A and B that their inputs match to this output. All right. So if C is in B, what does that mean about C?
Would we write it as like 144 divided by C equals some integer? Is that what we're going for?
Yeah, we don't need to get too technical. We can just say C is a positive factor of 144.
Oh, okay.
All right, and that means that C is equal to, let's see. Yeah, C, oh my goodness. C is equal to 2 to the x times 3 to the y. And let's also remember that 144 is equal to 2 to the 4th times 3 squared. All right, so what we can see here is that in order for C to be a positive factor of 144, then these exponents need to be less than or equal to the exponents that are used to make 144. So what are the different values that x can take if it can be anything less than or equal to 4?
0, 1, 2, 3.
Yeah, and then we'll also add 4. So that means that x is going to be in this set. And we can do the same thing with y. Y has to be less than or equal to 2, so y is in the set 0, 1, 2. Now these two sets are the same sets as we have for the cross product of A. So we can say that x, y is in the set A, which is our domain. So that means that we can say that there is some xy that if we plug it into our function, it's going to equal C. All right. Are there any questions on that? Okay, awesome. All right, so we have one more part for this problem, which is that we want to conclude something about the cardinality of both A and B. So does someone want to remind us what cardinality is?
It's the size, right?
Mm-hmm. Yeah, cardinality is how many elements are in a set. Okay, so does anyone want to take a guess at what we can say about the cardinality or explain how they got to that answer? All right, so there are a couple different ways to get to this point. So one of the ways we can get to it is that we know that F is 1 to 1. And from the textbook, that means that the number of elements in A, what was that? Okay, if that was an answer, I didn't hear it. I think someone just accidentally unmuted themselves. Okay, we'll keep going. If F is 1 to 1, then the number of elements in A is less than or equal to the number of elements in B. And if F is onto, then the number of elements in A is greater than or equal to the number of elements in B. And we saw that with our examples too. For onto, we see that the number of elements in A is, wait, what? I think that might have been written wrong. Number of elements in A. Yeah, I think this should be the other way around. If anyone can double check on that in the textbook, I don't have it right on me, but one of them is greater than, one of them is less than. And I believe from our example that it should be onto means that the number of elements in A is less than the number of elements in B. So please correct me if I am wrong.
1 to 1
All right.
is M is less than or equal to N. So
M is,
so for the first
so it
one,
should be the other way?
it should be swapped.
Okay.
The other way around.
All right. Okay, so if we know that, then what can we say about the number of elements? If it is both of these, then what does their relation have to be?
They're equal.
Yeah. And just out of curiosity, does anyone know what the cardinality of these two sets is?
Be 15.
Yeah, exactly. Because we have 5 elements in A, or 5 elements in this set, 3 elements in the other, multiply them because they are a cross product. So the number of elements in A is 15. So that means the number of elements in B is 15. All right, we're done with that problem. Any last minute questions before we move on? All right, on to relations. So for each of these sets, or each of these relations, we want to decide if it is reflexive, irreflexive, transitive, or antisymmetric. So let's just start with reflexive and start with R1. And remember the definitions of reflexive. Reflexive means that for every element A that's in the set, A is in the relation. Okay, so is R1 reflexive?
No.
Yeah, R1 is not reflexive because not all elements, or let's see, it'd be better to say not all letters immediately precede themselves. All right, and what about R2?
Also no.
For the same, not the same reason, but a similar reason. Not all letters precede themselves.
Wait, can you explain why there are not reflexive? I'm sorry.
Do you mean, sorry, not reflexive or irreflexive?
Why, like, because we're saying that they are not reflexive because not all letters immediately precede themselves. Like, can you explain that?
Yeah,
Or-
so the difference between these two sets, this, I'm actually not sure what that symbol is called. Anyway, I always get the Greek letters.
Alpha, maybe?
Alpha, and yeah, probably this is beta. Thank you. Okay, so alpha immediately precedes beta in alphabetical order. So that just means that some letter comes directly before another letter. So like X and Y X comes directly before Y in the alphabet. And the second one is that alpha comes before, but not necessarily immediately precedes it. So it could be X and Z because X does come before Z, even though it's not right next to it. Does that answer your question?
Yeah, thank you.
Okay. All right. And then we're saying not all letters. We know that no letters precede themselves, but in order to prove that it's not reflexive, we just have to say that not all of them do. Okay, so moving on to irreflexive. And irreflexive means that for every A in the set, it does not point back to itself. So that means that there is nothing that has a self loop in the relation. So is R1 irreflexive?
Yes.
Yes, because no letters immediately precede themselves. All right, and what about R2?
Yes.
Yeah. Because no letters come before themselves. All right. Halfway there. Let's go to transitive. And transitive means that for every A, B, and C in some set, if AB is in the relation and BC is also in the relation, then AC has to be in the relation. All right. So is R1 transitive?
Yes.
No.
Okay, we got
It-
conflicting answers
it's
here. Does anyone
immediate-
want to say why?
It's immediately precedes, so you would never have A points to C. It would only ever be A points to B.
Good point.
Exactly. And actually our definition is kind of our counterexample here, which is that A precedes B, or I'm just going to use IP for immediately precedes because that's a lot to write over and over again. So if A immediately precedes B and B immediately precedes C, but A does not immediately precede C because B is in between them. So no. All right. What about R2?
Yes.
Yeah. R2 is going to be transitive because if A precedes B and B precedes C, A still does precede C. And that's going to be the case for all of the rest of the alphabet. Okay, one more, which is antisymmetric. And the definition of antisymmetric is that for every A and B in the set, if A and B is in the relation and BA is in the relation, then A does not equal B, or whoops, A does equal B. Sorry about that. So that basically means that A can't point to B and B point to A unless they're the exact same element. All right. Is R1 antisymmetric?
No,
And how come?
because A can point to B, but B can't point to A.
That's correct, but that actually violates the hypothesis and not the conclusion, right? So B doesn't point to A. We don't have that in the relation at all, which means that automatically the whole implication has to be true. This was one of the ones that there were a lot of tricky questions like this on the pre-lecture quizzes, and we got a lot of questions on that. So if you were confused, here's the answer. It's that remember, just the rules of implication still are going to apply here. So the hypothesis fails. So yes, it is antisymmetric. All right. And what about R2?
I think the hypothesis also fails on that one for the same reason.
I think my Wi-Fi just went out, so I didn't hear everything that you said. Do you want to repeat it just one more time?
Oh, doesn't the hypothesis fail for the same reason?
Exactly. Hypothesis fails. So yes, because in both of these cases, B can't precede A, so it's not in the relation. All right, are there any questions on any of those? These aren't necessarily formal proofs. These are kind of just practices on relations. Okay. There is one more relation question, which is going to be a more formal proof of these. So we have an equivalence relation. We know that just because of the problem statement, but let's prove why it's an equivalence relation. We want to prove that R is reflexive, symmetric, and transitive, and then figure out what partition is induced, because we know that equivalence relations always produce partitions. So let's start by proving that R is reflexive, and I'm just going to throw up the definition of reflexive again, just so that we remember. Okay, so to start with a reflexive proof, we want to, let's just say that Z is in the set of integers. All right, and eventually we want to show that Z to Z is in the relation. So how would we accomplish that? What's our first step?
Can't you just show that Z minus Z is 0, which is divisible by 3?
Exactly. So Z minus Z is 0, and 3 does divide 0. So then Z has to be in the relation. And that means that R is reflexive. Does that make sense to everyone? All right. So let's move on to symmetric, which is, we didn't do this one in our last problem. So we want to show that for every A and B that's in A, that if A and B is in the relationship, it implies that BA is in the relationship. So let's go ahead and just let some XY be in the relationship. And we want to show eventually that YX is in the relation. Okay, similar to how we did it last time, we're just going to start by plugging in x minus y, except this time we know that it already is in the relationship. So we're going to set it equal to 3m, where m is an integer. Okay, if we're trying to eventually show that y points to x, or yeah, y points to x in the relationship, how can we kind of manipulate this equation to get where we want to be?
Should we multiply by -1 in both sides?
Yeah. So we'll have negative x plus y equals negative 3m. And if we rewrite this and do some factoring, we end up getting that y minus x equals 3 times negative m. And we can use closure to say that this is equal to 3n, and n is in the set of integers by closure. All right, and now we know that yx is in the relation by the definition of divisibility. And that means that R has to be symmetric. Any questions on that section? Okay, moving on. Finally, we have to show that R is transitive. And transitive is the big long definition with A, B, and C. So if A and B is in the relation and B and C is in the relation, then AC is in the relation. So let's start by using our hypothesis, and we're going to let x, y be in the relationship, and y, z is going to be in the relation as well. So that means x minus y equals 3m, where m is in the set of integers, and y minus z is equal to 3n, where n is in the set of integers. Okay, anyone have a guess what we want to do next in order to remember that we're trying to show that x, z is in the relation?
Substitution, right?
We can substitute either, well, let me first ask, which variable do we want to substitute?
Y?
Yeah, and we can take y from either of these, plug them into either of the other equations. But we'll just do, let's see, the one that comes to me quickest is 3n plus z. And we can plug this into this side and get x minus 3n plus z equals 3m by substitution. Whoops, that was weird, you. Okay. So now we can kind of rearrange everything here, and we end up with x minus z is going to end up being 3m plus 3n. What can we do next?
Factor the 3.
X minus z is 3 times m plus n, which means that x minus z is equal to 3, let's say c, where c is in the set of integers by closure. And then by definition of divisibility, we have that x, z is in the relationship, so R is transitive. Okay, so we've proved that R is an equivalence relationship. So now we want to figure out what is the partition that is induced by the equivalence relation. So we'll let Z equal some sets. What are those 3 sets going to be?
Would it be x minus y divisible by 0, 1, and 2?
Exactly. So P0 is going to be z's in a set of integers such that z equals 3n for n is in a set of integers. P1 is going to be similar, but z equals 3n plus 1. And P2 is going to be our last remainder, z equals 3n plus 2, for n is in a set of integers. All right, got another one done. Any questions on that? Okay, let's move on to a counting problem.
Hey,
I love combinatorics, so.
Sorry, I had one question.
Okay.
This is probably the fact, maybe just that I'm just tired, but how does wouldn't it be a valid, if you go back to the previous problem, wouldn't it be a valid partition to have just the numbers that are divisible by 3 and then the numbers that aren't divisible by 3? Like, how do you conclude that there's 3 of them?
That is a good question. Whoever, let's see, I think it was Subi said the partitions. Do you want to explain why you got that answer? How you figured it out?
Basically, because like 0 through 2 is like every integer up to like the one that's divisible by 3. Something like that. I don't know. I kind of just like sort of guessed. I got it right because like usually
Okay, that's totally fine.
things that are divisible use it to the remainder
So-
of the class.
So remember, so we have x minus y is divisible by 3. So if you took everything that wasn't divisible by 3, then subtracting them wouldn't necessarily get you a result that's divisible by 3. Does that make sense?
Right. Yeah, my question was just.
So that's really what these partitions are.
Oh, okay. Yeah. My question was.
So yeah,
just,
a partition is. Sorry,
Um,
you go ahead.
yeah, no, it was just you'd still have 2 valid partitions if you just had P0 is everything where z equals 3n, and then P1 is everything where z doesn't equal 3n, or where like, something like that.
Well, let's just go ahead and say, let's say that n equals 1. And so we have, let's see, z equals 3 times 1 plus 1 is going to end up being 5. Or z equals 3 times 1 plus 2. Oh, whoops. 3 times 1 plus 1 is not 5. It's 4. I'm tired as well. I totally get you. Okay, then z equals 5. So if we did this relation on itself, we would have either 4 minus 5, which equals -1, or 5 minus 4, which equals 1. And 1 is not divisible by 3. Right? So that means that they wouldn't be in the partition together. Because the way that partitions work on equivalence relations is basically all the numbers in this partition, if you subtract them from each other, it will be divisible by 3. All the numbers in this partition, same deal. But if you combine them and they're not divisible by 3, there you go. Yeah. If the difference isn't divisible by 3, then they can't be in the same partition together.
Okay, I totally forgot about the fact that it was the difference is divisible by 3, and we've done problems like this before, so yeah, that makes sense.
Okay, awesome. All right, counting, combinatorics, very exciting. I think combinatorics are awesome. Not everyone agrees with that, but I think they're fun. So we have a best of 5 tennis match with two players that are A and B. And the letters A and B indicate a set won by one of those players. And the first letter refers to the first set, the second letter to the second set, and so on. So we've got a few different questions about this. Let's just go through them one by one. So how many ways are there for the match to end after 3 games? And remember that this is a best of 5.
There's only 2.
Yeah, there's 2 ways, because after somebody hits 3, if they've won all 3 sets, it's over. So in order for the match to end after 3 games, one person has to win all 3. So our options are either AAA or BBB. Okay. Next one, let's start with B. How many ways are there for player A to win in exactly 4 games? Does anyone want to say what one sequence that would mean that A wins after 4 games?
AABA.
Okay. Anybody else?
ABAA.
Mhm.
A, B, A, A.
BB.
All right.
No, it's all right. Or B.
A.
Yes. Okay, and that's actually all of them. So there are 3. Then C asks why the answer for part B is the same as the answer to the question, how many ordered lists of length blank taken from the set that includes AB have exactly blank A's. So we need to fill in these blanks and also understand why that question is the same. Does anyone have a guess?
4 and 3.
That is the instinct.
Oh, 3 and 2.
Yeah, exactly. So the reason for that is we know that we have 4 games, and we know that in order for it to end at the 4th game, that this last space has to be an A. So we end up with 3 blanks, and we need exactly 2 of them so that A can win 3 games. So that's how we get that answer.
So is that the reason why we cannot have like AAAB? Because that would
Yeah,
still
exactly.
okay.
Yeah, because then the A would win after the 3rd game, so B actually wouldn't play again. The game would already be over. Okay, does that make sense to everyone?
Yeah.
Okay, our
Yeah.
next few questions are going to be, or our next 2 questions are really similar. But this time, D is asking how many ways are there for player A to win in exactly 5 games? So let's do the same thing. If you have a sequence that would work, go ahead and shout it out.
BBAAA.
All right.
BA BAAA.
BAA. Yep. Okay, I'll give you a hint. There's 4 more left.
Doesn't the top one have too many A's?
Yes, it does. Thank you. Got a little carried away there.
BAABA.
All right.
AABBA.
A, B, B, A.
A. Can we do also ABBAAA?
A, B, B, just 2 A's after, but yeah.
ABABA.
Yep. So that is all of them. We end up with 6 of them. And again, we want to fill in these blanks. So what are these ones going to be?
Four and two.
Yeah. We still are going to end with A. So, but if we're ending with A, we still can only have 2 more A's, but we have 4 different places to put them.
Can you explain why it's 1 less than what the expected thing would be?
Yeah, so because once A hits 3 wins, right, the game is over. So if we just took length 5 and we said, let's find 3 A's, then the 3 A's could be right there. But that would mean that A actually wins after 4 games instead of 5. So we have to assume, whoops, didn't mean to erase that. So we have to start by saying that, oh my gosh, why do I keep pressing the wrong thing? Okay, we have to start by saying that A is in the last slot. We know that it has to be in the 5th position or else the game would end sooner. So it's almost like this last one isn't even there. We're not even really considering it because we know what it has to be. So we end up with just 4 blanks and we know that 2 A's have to be in there. Does that make more sense?
I see.
Okay. All right, any other questions? All right, so that I believe is actually our last problem that we had blocked out for today. So feel free to take off a few minutes early, and you can also stick around if you want to go over any other problems.
Can we do a homework problem?
Yeah.
I just need to,
Which homework?
understand it. Like number 8, it's all about like compositions, but we didn't really talk about them very much during the lecture, so I'm still confused on.
I was going to ask that same question.
Okay, so we want to see, this is homework 4, yes?
Yeah.
Okay, homework, let me just pull it up real quick and then. And you said problem number 8?
Yeah.
Problem 8. Slowly but surely loading. Okay. So I'm not going to go through A, B, and C. Is there one that you specifically want to look at?
Yeah, just one of them is fine. I guess just A.
So 8A. You want to show if if R is a reflexive relation on A, then the composition is a reflexive relation on A as well. Okay. So let me just read through it real quick because I haven't gone through this one. Okay. All right, so let's start by, let's see, we want to show eventually that the composition is a reflexive relation. So let's just assume, well, okay. Let's start by letting some Mn be in the composition of R. All right, so what does this mean about R? What can we say M is related to in R?
Itself. Right.
That is true, yes. So M is in R, but there's something else that we can say because it is a composition of R, then there are a few different things that have to be in R in order for the composition to be true. So we're going to have some other element, let's just call it X, and we're just going to say that that's in R, So then what does X have to be related to?
M.
N. All right, and we know that that's true because otherwise M would not be related to N in the composition. We have to have something in between. If we had these, that means M is in here, N is in here. Some element here has to connect them. So we're just calling that X. Okay, and we also know that R is reflexive, like you said. So M is equal to itself, but also we know that X, like if M is related to M, then X can be equal to M and N can be equal to M. So let's actually just set all of them equal to some other letter, which is A. Does that part make sense? Okay, so now what can we say about A in R?
It's an element of R.
Yeah, and what is it related to?
A.
So A has to be related to A in R because we know that it's reflexive. Okay, we're almost there. So there's something else that is, let's see. This seems repetitive, but it's worth saying. A is related to A and A is related to A. So similar to how we made this jump, so let's draw another diagram. So A is related to A, because this is R. And this is also R. A is related to A. So what can we say about the composition?
Just for clarification, composition is when you plug it like another function into another function, and since they're the same, it'd just be plugging the function into itself. So then would the first A point to the third A?
Yeah. And it's a little bit different with relations because there's usually not like a formula to plug it into. That's usually more the case with functions than relations. We saw in lecture the relations today were, or not lecture, but in discussion, we saw that the first relation was about the alphabet and the second one was about being divisible by 3. So they won't necessarily be functions. But we can still always say that R times R, A is going to be related to A. Okay, so what does this tell us about R composed with R?
It's reflexive.
Yeah. So I find when I'm doing these problems, the biggest help is to just keep drawing pictures like this to understand what's going on, because sometimes it can get a little bit confusing, but that helps me figure out how these relations have to work. So does that all make sense? Do you feel like you can tackle B and C?
Yeah.
Okay. And remember, if you're having any other issues, you can always come to office hours for any other clarifications once you've tried B and C. All right, let's see. Oh, I just realized we are still live to YouTube. Nancy, do you want to